In the vast expanse of space, the relationship between Earth and its celestial companion, the Moon, has always been a subject of fascination. While we've long understood the Moon's influence on Earth's tides and rhythms, recent discoveries have revealed an unexpected way in which our planet affects its lunar neighbor. Earth is making the Moon rust. The surprising discovery of lunar rust. In 2020, scientists made a startling discovery that challenged our understanding of lunar chemistry. They found evidence of hematite, a form of iron oxide commonly known as rust, on the Moon's surface. This finding was perplexing for several reasons. Rust formation typically requires the presence of both water and oxygen, neither of which are abundant on the Moon. The Apollo missions, which brought back numerous Moon rocks for study, had never found definitive evidence of oxidized iron. The Moon's lack of a substantial atmosphere and magnetic field leaves it exposed to the solar wind, which typically prevents rust formation. To understand the significance of this discovery, we need to delve into the chemistry of rust formation and the unique conditions of the lunar environment. The chemistry of rust. Rust is formed through a process called oxidation, where iron atoms lose electrons to oxygen atoms. On Earth, this process is common due to the abundance of oxygen in our atmosphere and the presence of water. However, the Moon's environment is vastly different. It has virtually no atmosphere. Liquid water is not present on its surface. It lacks a strong magnetic field to shield it from the solar wind. The solar wind, a stream of charged particles emitted by the sun, typically acts as a reducer, undoing the oxidation process. This makes the presence of rust on the Moon even more puzzling. Earth's magnetotail, a cosmic shield. The key to understanding lunar rust formation lies in Earth's magnetic field. Our planet's magnetic field isn't a perfect sphere. It's deformed by the solar wind into a teardrop shape with a long tail called the magnetotail. This tail stretches far enough to encompass the Moon for about 5 days each month. During this time, the magnetotail serves two crucial functions. It shields the Moon from the solar wind, temporarily preventing the reduction of any oxidized iron. It acts as a conduit for particles from Earth's upper atmosphere to reach the lunar surface. Earth's contribution. Oxygen and water. Research has shown that Earth plays a vital role in providing the necessary ingredients for rust formation on the Moon. Oxygen supply. A 2017 study published in Nature Astronomy estimated that tens of thousands of oxygen ions from Earth's upper atmosphere are implanted into the Moon every second. This occurs when the Moon passes through Earth's magnetotail, which flings these charged particles towards the lunar surface. Water formation. While some water on the Moon is thought to form when solar wind protons interact with oxygen-bearing minerals, a 2023 study suggested an additional mechanism. The research found that water formation rates on the Moon didn't decrease when it was shielded from the solar wind by Earth's magnetotail. The study hypothesized that electrons swept along with the oxygen ions from Earth could trigger chemical reactions in lunar soil, producing water. This water can then react with iron to form hematite. Implications in future research. The discovery of Earth-induced rust on the Moon has several fascinating implications. Lunar atmospheric record. The oxygen implanted in the Moon's surface could potentially serve as a record of Earth's ancient atmosphere. By studying lunar samples, scientists might gain insights into the composition of our planet's atmosphere over billions of years. Interplanetary interactions. This finding demonstrates the complex and often surprising ways in which celestial bodies can interact, even across vast distances. Resource potential. Understanding the processes that create water on the Moon could be crucial for future lunar exploration and potential colonization efforts. Planetary protection. The exchange of materials between Earth and the Moon raises questions about planetary protection protocols and how we might inadvertently affect other celestial bodies in our solar system. Challenges in studying lunar rust. Despite the exciting nature of this discovery, studying lunar rust formation presents several challenges. Limited samples. Most of our lunar samples come from the Apollo missions, which explored only a small portion of the Moon's surface. Remote sensing limitations. While orbital instruments can detect the presence of hematite, they can't provide the detailed analysis possible with physical samples. Temporal variations. The cyclical nature of the Moon's passage through Earth's magnetotail means that rust formation likely varies over time, making it challenging to study consistently. Competing processes: the constant bombardment of the lunar surface by micrometeorites and the solar wind outside of the magnetotail's protection can potentially erase or alter evidence of rust formation. Future exploration and research directions: the discovery of lunar rust opens up several avenues for future research. Targeted sample return missions: future lunar missions could target areas where hematite has been detected to collect samples for detailed analysis on Earth. Long-term monitoring: placing instruments on the lunar surface to monitor rust formation over extended periods could provide valuable data on the process and its variations. Comparative planetology: studying rust formation on the Moon could inform our understanding of similar processes on other airless bodies in the solar system. Advanced remote sensing: developing more sophisticated orbital instruments could enhance our ability to study lunar chemistry without the need for physical samples. Experimental simulations: creating laboratory setups that mimic the conditions of the Earth-Moon system could allow for controlled studies of rust formation under lunar-like conditions. Conclusion: the discovery that Earth is causing the Moon to rust is a remarkable example of the interconnectedness of our cosmic neighborhood. It challenges our understanding of planetary interactions and demonstrates that even in the vacuum of space, our planet's influence extends far beyond its atmosphere. This finding not only sheds light on the complex chemistry occurring on the lunar surface, but also opens up new possibilities for studying Earth's own history. The Moon, acting as a repository for particles from our ancient atmosphere, could provide a unique window into our planet's past. As we continue to explore and study our celestial companion, we're likely to uncover more surprises. The story of lunar rust serves as a reminder that in space science, as in many fields, some of the most exciting discoveries come from unexpected places. It underscores the importance of continued lunar exploration and the potential insights we can gain about our own planet by studying its cosmic dance partner. The rust on the Moon, formed through Earth's distant touch, is a testament to the intricate and beautiful ways in which the bodies in our solar system interact. It's a cosmic connection, written in iron oxide, linking our world with the silvery orb that has fascinated humanity for millennia.